so day 2 is what we're going to actually talk about in class, and it's talking about translations, and we have a couple types that we're going to talk about. We're going to talk about vertical and horizontal. We're going to talk about when we reflect over the x and y axis. We're going to talk about dilations and absolute value, all of these guys. So the first one I want to talk about is vertical and horizontal translations. And it says the graph of g of x is equal to f of x plus k, and the graph is translated. So if this right here means that you're translating it either up or down, okay? If k is positive, then you are shifting up. If k is negative, then you're shifting down. And these two graphs show, so here is f of x, and then this is right here, this graph, f of x shifted up k. And then this is f of x shifted down k. All right, horizontal reflections are opposite of what you think. So the minus right here is giving us that clue that we got to be careful when we're doing this. So it is opposite of what do you think? We call it counterintuitive. So when you move to the right, when this is negative inside, you're actually moving to the right. When you have this positive, when your h is added, then you're going to be moving to the left. So it's opposite of what you think. You see this minus and you want to go to the left, but you're going to go to the right. Then we have horizontal and vertical dilations. These are stretches and shrinks, or stretches and compressions. Or I guess our textbooks uses expand vertically or compressed. So anytime you're dealing with your vertical issues, these are exactly what you think. So this is, if a is bigger than 1, then this would be a stretch or an expand. And it's kind of like taking that f of x and like pulling it, so it's like expanding it up. And then you have the, when a is between 0 and 1, this would be a compression. So it's like you're taking this parabola right here and you're pushing it down, you're compressing it. I also call it a shrink. Horizontal dilations are, once again, opposite of what you think. So when you have an a in here, if your a is bigger than what, bigger than 1, so like you have f of, let's say 2x, then with these two graphs, what you're looking at is this isn't actually stretching it horizontally by 2, it's actually compressing it by 1/2. And if you had a fraction, so let's say you had that inside the parentheses, then that's not shrinking it by 1/2, it is actually expanding by 2. So it's opposite, anytime you're dealing with horizontal, it's opposite of what you think. Absolute value is kind of weird to look at. If this was your f of x right here, if you were to do the absolute value, see how they have absolute value and they put f of x in here? What that means is you have absolutely no negative numbers, because absolute value is your distance from 0. So it's a distance. It's just describing how far from 0 you are. So you have absolutely no negatives. So it just kind of flings all those negatives from right here and puts them up here. This one does a little weird graph, and it says basically the transformation results in a portion of the graph that is to left and then is reflected a portion onto the y values. So it really is kind of weird, but it's taking your negative values and your negative values over here, and it's kind of like reflecting them over here. We don't do that too much in on-level pre-cal, but they're just nice to be able to see if you do have that opportunity. And I guess I missed something. I missed the reflections. So we have reflections. So when you reflect over the x-axis, if you notice, that's outside of the equation. So you have your equation here, and when you reflect over the x-axis, you have your negative in the outside of the equation. When you reflect over the y-axis, notice that your negative is actually inside the equation. All right, so how do we do these in class, and what is your work that you're using to prove that these translations are occurring and what's actually happening? And so we're going to use the graph f of x is equal to x to the third, and that's going to be our parent function. And so what we're going to do is we're going to provide these translations to this graph. So here's how we do it. We set this up. We have our x and we have our y, and we do our parent function. And you have to understand all the parent functions really well. So you have -1, 0, and 1. When you cube -1, you get -1. When you cube 0, you get 0. When you cube 1, you get 1. So this graph right here does this. Okay? Now, what we're going to do is we're going to look at this graph here, this translation, and what this is saying is this -5 is a vertical change. It is shifting this graph down 5. So that's going to affect my y values. So each one of these y values are going to go down by 5. So this is -6, -5, and this would be -4. So these are my new points. So -1, -6. And it's my iPad, so it's not the greatest. And then 1, 4. And so there is my new graph, which obviously goes on forever. So this is your work to verify this graph. Very important that you have that table. Okay, so we're still using the same table, but now we're going to look at a horizontal change. I'm still going to use the same 3 points. Okay, so we're going to continue on with all the different transformations. And remember I told you outside is a vertical and inside an actual equation, because if you can picture it, the parent function was x to the third. X minus 3 is occurring inside that equation. So that's going to be related to our x value. And so we're going to put x minus 3 here, okay? And then this is showing that it's moving to the right 3, but we're going to algebraically prove that it moved to the right 3. Basically what you're going to do is you're going to set up this x minus 3, and you're going to set it equal to each of your x values. And if you notice, you are adding 3, which is right. Would move you to the right. So x is equal to 2. X minus 3 equals 0, so plus 3, x is equal to 3. And now you can kind of get the point, so this would be 4. So I forgot to graph the parent function. Let's see. The parent function looks like that. And then this guy would be 2, -1, 3, 0, and 4. So it would look like that. So it shifted it to the right. C has two things occurring. One is vertical and one is horizontal. So we're going to start with the parent function table. I almost wrote the table wrong. I'm going to do that. All right, so you always, usually you can start with your vertical first. This is shifting this graph up 4, so that's dealing with the y. So I'm going to come over here in the y column and add 4. So 4 plus a -1 would give me 3. That's 4. That's 5. Then on the other side, I'm dealing with the a horizontal change. And I'm going to write it on the x side because the x would be your horizontal axis. And we're going to set each of those equal to x plus 2 is equal to each of these x's. So if you notice, we subtracted, so that moves it to the left. And that'll give me -3. And that's going to give me -2, and then that would give me -1. Once you see the pattern, you don't have to continue drawing or doing the equations. This is the new equation. This is what we just transformed. So -3, 3, and -2, 4, and -1, 5. So there it goes. So that took that graph and it shifted it to the left 2, and it shifted up 4. All right, how do you show that you're reflecting when you are not given a graph? Well, here's what you do. When you reflect over the x-axis, you are simply going to put a negative in front of the equation. This is going to reflect over the x-axis. So really for the first one, we're just going to do this. And we reflect over the x-axis. And then basically you can just put the negative with the top, or you can do the negative to the bottom. It won't matter, but as long as you're basically multiplying with -1, like if you think about a fraction, -1 over 1, and I'm just going to multiply my numerators. So when you multiply your numerators, you need to do the distributive property. So this did shift it across the x-axis. So to have that shifted across the x-axis or reflected, you have to put a negative outside of it. With the when you are flipping it over the y-axis, you actually have to plug a -x in for every x. So that looks like this. And that's kind of like what we were doing with odd and even, so you should be kind of familiar with it. Oops. And then you simplify. So this will give you -5x minus 9, and then this is going to give us x squared plus 3. There's no testing whether it's odd or even, this is what a reflection over the y-axis would be. All right, that's that page. And I think I just need the bottom for this one. I just need example 3. So I'm going to use this page, even though I had that one on the top part. It says the graph of x squared, y equals x squared, undergoes the following transformations. And we need to write the equation with these results. So if we took the parent function x squared and we shifted it to the right 2, that would look like that. Horizontal is opposite what you would think. To go to the right, you'd want it to be positive, but it'll be opposite. To do a vertical stretch of a factor of 3 would give me this. and then a vertical translation up. Then it says apply these rules in an opposite order to find the result. So now we're going to go opposite order. You have this if you have the notes printed off, but I don't. So the first one is going to be this. Okay, so in opposite order, that's going to give me y equals x squared plus 5. If I want to vertically shift that by, stretch that by 3, then I have to use that whole equation and multiply it, which would give me 3x squared plus 15 when you do the distributive property. Then shifting that equation to the right 3 would give me so these turn out completely different if you look at them. Just because of the order in which you're going. So you got to make sure you're watching the order in which you're doing it. All right. Last one is piecewise. Oh, I actually wanted to do what I was doing and I didn't do it. Okay, piecewise graphs. We talked about them a little bit at the beginning of the school year, but you need to be familiar with graphing these fairly quickly when you're doing this. So what you do is you basically graph this equation right here, the x minus 5, and that's a linear equation. So you're going to go down to negative 5 and go up 1, and I'm on my iPad, so this isn't going to be great because I can't quite get them to line up the dots. Okay, so this would be the equation for x minus 5 equals y. But I only want to graph the points bigger or less than 0. So I really need to erase all of these. So this graph is doing that. And it is a closed dot at that 5 because that has a line underneath that inequality. X to the third graphs, remember that graph we did here that does this? And it had 1, negative 1, 1, negative 1, 0, 0, and 1, 1. And it also has 2, 8, because if you did 2 times 2 times 2, you would get 8. But I only want to graph the numbers between 0 and 2. So I really only want to graph, and that should be an open circle. I only want to graph that right there. At the 2, at x equaling 2, it needs to be a closed dot because there's a line underneath that inequality. And then this is going to graph a rational function. Like that. But I only want to graph the numbers bigger than 2. So at 2, when I plug 2 in, I get 1. So I'm going to put a dot at 1, which happens to be on that other guy. It is being filled, that open circle is being filled by this graph right here. And I'm just basically going to do that. Okay, so this is a transformation. It took the parabola, this one, and it shifted it to the left 6. And if you can think about the parent function of a parabola, you would have negative 1, 1, 0, 1, 0, 0, and 1, 1. And I'm just plugging it into x squared. But I'm going to shift each of these points 6 to the left. So this point right here would be right here. And this would be the parabola, right? It would look like that. So I just shifted that parabola over. This is saying I'm only wanting the x's less than negative 5. So I have to erase everybody that is below or above negative 5. And at negative 5, I need to have an open circle because that doesn't have a line underneath it, even though I just drew a line. Then the other part is saying that we have a 7, and we're going to be a constant 7 from negative 5 to x is less than or equal to 2. So right here is 7, so we're going to be a dot here, and we're going to go all the way to 2, and that's a dot. Both of those are closed dots. I'm going to rewrite this equation. I would like to make it a little bit easier where it's just doing a simple transformation, so I'm not going to have this equation. I want you to cross it off and put this. Okay, I want to do a simple transformation. So absolute value looks like this. And it's pretty much the exact same points that you have for a quadratic. The only difference is it's very sharp. So this would be the absolute value of that, of the parent function, this. But we're going to shift it to the right 4. So we're going to take each of these points and go over 4. And you basically go up, shift all those points. Okay? And it's saying that we want to graph all the numbers bigger than 2. And so that would be right here. If I can get that in. And this would be an open circle. So there's your piecewise.